Welcome to the Mechatronics Revolution Fundamentals and Core Concepts. In this lesson, we'll talk about signal conditioning circuits. The objectives of this lesson are to identify the role of signal conditioning circuits in sensor integration and processing. We'll talk about low-pass filters using analog circuit components. Then we'll talk about the design of low-pass filters using software. And finally, we'll look at some simple methods to reduce bias from a signal. So here we have our inverted pendulum robot. Now this robot uses accelerometers in order to sense whether it's upright. And it needs these accelerometer signals in order to maintain itself in that upright position. But we can't use the accelerometer feedback directly. In fact, if we did so, the robot actually wouldn't work. Instead, we have to filter that feedback, filter that sensor data, in order to get a clean signal that's useful for the control algorithm that keeps this upright. So in this lesson, we'll learn more about those filtering algorithms that we'll often need to apply to sensors in mechatronic devices. So why do we need signal conditioning circuits? Let's look at a few examples. First, here's actual data from a 3-axis gyroscope. The signal itself should be quite smooth because the motion of the object that it's attached to is quite smooth. However, this high-frequency noise corrupts the signal, and you can see the fast, high-frequency noise embedded within that signal. If we read that signal directly, then a lot of times we won't get good performance with the system if we try to use that data for some type of control or action. Instead, we'll usually get better performance if we filter out some of that noise before we use the signal for anything. Doing that typically requires a low-pass filter. Here's another example. This is actual data from a thermopile sensor, and it's attached to an object that rotates, looking at the sky and the ground and the sky and the ground repeatedly. And the sky and the ground look to be different temperatures, and as a result, it creates this sine wave signal, which if you zoom in on this signal, you can see. However, the temperature of this device changes over time. And as the temperature changes, it introduces this moving bias to the signal. The signal that we want to use for our system is this high-frequency sine wave. And thus, we need to remove this changing bias before we read it in the microcontroller. This type of operation requires a high-pass filter instead of a low-pass filter, and we'll talk about that. So we've seen that signal conditioning is often a necessary aspect of sensor integration on a mechatronic device. There's two major components of signal conditioning. First is amplifying the sensor outputs to an appropriate voltage range so that we can read it with our microcontroller. The second aspect is reducing noise or bias in the signal, so changing the output signal characteristics before we use the data for anything. Microcontrollers typically read analog signals from analog sensors using a device called an analog to digital converter. Oftentimes, the output range of a sensor won't be compatible directly with the range that this ADC expects. And so we'll need to either amplify the voltage from the sensor or we'll need to reduce the voltage output from the sensor to the range we need. We've already discussed how to amplify signals using op-amp circuits. And we've already talked about reducing voltages using a voltage divider. And you can see diagrams of those two devices here. These are the exact devices you would use when taking sensor data and either amplifying it or reducing it. So we can use these circuits directly for that purpose. Now that we know how to amplify or reduce voltage signals, let's talk about the second aspect of signal conditioning, which is filtering and changing the bias. So filtering is the process of attenuating unwanted components of the signal while allowing the components that we want to pass through. So the filter just removes the unwanted components. What are these unwanted components? Well, they might be noise in a signal, or they might be bias, or they might be both. And at the bottom of the slide, you'll see some graphs. You'll see a signal that's noisy and you'll see a signal that's what we call biased. If we have a desired or an actual value of our signal, say around 2, our signal that we measure might be up closer to 5, and there's a bias that's causing that. Low-pass filters act to attenuate or remove high-frequency content from the signal. A lot of times for mechatronic devices, noise manifests itself as this high-frequency component. So we usually want to remove high-frequency noise. Low-pass filters are what we use to do that. Here's a circuit that we can use to remove high-frequency noise. It's called a low-pass filter, or an RC circuit. It's a passive circuit, meaning we don't have to power it, and it consists of just a resistor and a capacitor, where the capacitor is placed as shown in the diagram. The nice part about this passive circuit is it doesn't require external power. And there's a key value that we need to understand the performance of this filter, and that's that time constant tau. Tau is computed as the resistance times the capacitance of the elements that we use. Another type of low-pass filter is an active low-pass filter. Here we use an op-amp. So this both amplifies the signal and filters the input signal. The time constant of this filter is tau, again, which is equal to R2, the resistance value of R2, times the capacitance value C. Likewise, the amount that it amplifies a signal, or the gain, is equal to R2 over R1. And you can see in this circuit, as well as the circuit on the previous slide, the passive filter, where you plug in the input voltage from the sensor, and then where you take the output from the filter. So I've highlighted both V input and V output on these two diagrams. Let's talk about the meaning of this time constant tau. A higher value of tau means that more noise will be attenuated, but you don't get that for free. The filtered signal will lag the actual signal more, and I'll show an example of that in a minute. A lower value of tau means that less of the noise will be attenuated, so we won't be able to get rid of as much noise, but we won't have that problem with lag in our filtered signal. So we have that trade-off between being able to get rid of more noise, but then inducing more lag in our filtered signal. Let's see how that works. Here's a noisy signal. So in blue, I have the perfect signal. That's what the actual value of what we're trying to measure is. The purple value is a value that the sensor measures directly. And you can see that we have quite a bit of high-frequency noise here that we want to get rid of. So the equation that I use to generate this pretend signal is shown in the box down there labeled sensor. If we put that data, this pink data, through a low-pass filter, we get this signal Y star. So let's look at the filtered signal that we get, the output voltage signal, with this pink signal sent in as the input. If we use a certain resistor and capacitor that gives us tau equals 10 milliseconds, then we get the signal at the top. So that's the filtered output that we would get, and you can see that we attenuate the noise pretty well, and we don't have too much lag. Now if we increase the filter time constant tau, so we use either a bigger resistor or a bigger capacitor, then you can see we get rid of even more noise on the bottom right, but now we have significant lag. And so that lag, you can see the black line lags the blue line. That lag can actually cause a problem in performance of our system. We might not see very good response or closed loop performance if we implemented that in some type of control system. So that lag may be a problem, or it may not be, depending on the application, but we have to be mindful that it's there. Just like using circuitry, instead we can implement a low-pass filter in software. So instead of implementing this filter using circuit components, we can implement it in lines of code. Here's the example of how we would do that. So here's a formula where we can take raw sensor data, and I've labeled that raw sensor data X. If we take X at a certain input time K, and we multiply it times the constant 1 minus alpha. Then we add alpha times the last filter output, yk minus 1. That's going to be our current filtered signal yk. So this equation is called a recursive equation, and it allows us to take raw sensor data and filter it in software. So the values y here would be the filtered signal, and the values x would be the raw sensor data. And if at every sensor measurement you use this equation to compute the filtered signal, then you'll have a low-pass filter that you can implement in software. There's a couple things you can choose here. Number one is the sampling interval, big T. Big T is how often you get a new sensor measurement. So that's your sensor update rate, how often you take a new measurement. The other thing you can set is that filter time constant tau. So you can choose a tau value, and then you can compute, as using the equation shown here, the constant alpha. And then you can plug that in the equation. So the time constant tau is a value now that you get to select in software rather than designing it using resistors or capacitors. Here's an example of that same sensor data that we used on the last slide, digitally filtering it or filtering it in software with a time constant tau of 15 milliseconds. And you can see that again, we get pretty good filtering performance. So this is all done in software with no need for additional circuit components. A final topic that we want to mention is removing biases from a signal. A DC bias is a fixed voltage offset that we want to remove. For instance, suppose we have a certain sensor and it produces an output of 1 volt when it reads an input of 0. So maybe 0 temperature or 0 acceleration or something like that. So suppose we wanted it instead to output 0 volts when reading an input of 0. What type of circuit will we need to do this so that the output is 0 when the input is 0? And we can see an example of what I'm talking about here, where we have a desired value of 0 and a measured signal of 1. To do that, we'll use a high-pass filter instead of a low-pass filter. This high-pass filter is also an RC circuit, except if you compare it with our passive low-pass filter, we've just switched the position of the capacitor and the resistor. So now, if we put our input here, V input as our raw signal, then our output signal will have the bias removed from it. So now, if we put the signal through, we'll see that the unbiased signal here that we want is actually at 0. So to summarize what we've talked about, sensor signals oftentimes require some type of signal conditioning before we can use them directly within a mechatronic device. We can use signal conditioning circuits to amplify a signal, or to reduce the voltage level, or to reduce noise or remove bias, or some combination of all of these. Low-pass filters are used to remove noise in signals, and we can build low-pass filters from either active or passive circuit components, or we can also implement them in software. Likewise, high-pass filters are used to remove DC bias from a signal and are built from a simple RC circuit.